Hi Aniruddhan.
Hi Bobby.
So we will continue solving some of the
Sure.
Bode
We
plots.
will do one or two more examples.
Yes. Yes.
Okay.
Yes.
Okay.
So
Shall I suggest some?
yeah, please suggest.
Okay. So we'll do something. We have seen cases where we had some gain, frequency independent, some zeros, some poles.
Correct.
I'll suggest another example like that.
Yeah.
So let us say h of s, the transfer function, is equal to 200 times s plus 20
S plus 20.
divided by
Yeah.
s into
Yeah.
2s plus 1
2s plus 1
into s plus 40.
into s plus 40. So there is a 0 and 3 poles.
Correct.
Very similar to our previous question.
Very similar to the previous question.
So the first step would be to write it in the form 1 plus
Correct.
s by z1 or
That's right.
yeah. So this means I'll take the 20 outside.
Yes.
1 plus s by 20 yes. So this is 1 plus s by 0.5
Correct.
into 1 plus s by 40. So I should bring the 40 out.
Correct.
Here is this correct?
Correct.
Yeah.
Yeah.
Because 2s I can just write it as s by 1 by 2.
Correct.
So this means some of the zeros will get cancelled.
Yes. Correct.
So this will become 100.
100.
And then the next step was to write h of j omega.
Correct.
In fact, we are just repeating the, it's for, yeah, it's almost similar question,
Correct.
I think. Plus j omega by 20
Correct. Yeah, this is a very similar thing because last time also we had 1 0,
Yes.
1 pole at the origin and
Yes.
2 poles otherwise.
Correct, correct. And a constant here.
And a constant k. Correct.
So we will individually draw.
Sure.
So for, maybe I will draw here itself. So for the 100, this will give a constant 20 log 100 to the base 10, which is
40.
40. So means there is a constant
value of
term.
40 dB.
Correct.
That gets added.
Yes.
Correct.
Then the 1 plus j omega by 20 so till 20
Yes.
it's a log 1, so 0.
0. Correct.
From then onwards, as the frequency increases, this is going to increase.
So because it's a 0,
Correct.
it will go up at 20 dB per decade.
Exactly. Then for the j omega, which is a pole.
Yes.
So Z1 P1. So I think this one we have dealt with in the previous question also.
Correct.
Uh,
So this will just be a straight line
correct.
with minus 20 dB per decade.
Exactly. And it will pass through log 1
So log 1, which is 0 dB.
0 dB.
Correct.
So I can write omega equal to
Correct.
1.
Correct. Maybe you can put the one little, because 20 is here, no?
Yeah, it's
We'll move it a little bit to the left.
yeah.
And we also have to leave space for 0.5. Right?
Yeah.
So
Yeah, it will not be omega. Individual omega plots will not
plots
be.
may not be, it's
may
not,
not
it's
be,
hard not
yeah,
to draw it
to the scale.
to
Yeah.
the scale. Correct. Yes.
Then P2. Which is the term 1 plus j omega by 0.5. Yeah, as you said, 1 and 0.5 are coming
Yes. Correct.
almost near. So maybe.
But on a log scale, that's what will happen, no?
Correct.
I think.
Will be
0.5
crowded.
Will be crowded.
Yeah, I think students should see, maybe just Google and see some of the,
Correct.
in fact, Bode plot itself, some samples, so they know then what the log plot will look like.
That's true.
So this is also a pole.
Correct. So it will be 0
So,
dB till 0.5
Yes,
and then minus 20 dB
minus
per
20
decade.
dB per decade.
Correct.
Then we just have one more term.
P3.
J omega by 40. So 20 is somewhere here.
Also 40 is going to be there. Correct.
So again till 40 it is 0.
Correct.
Then at minus 20 dB.
Perfect. Perfect. Yeah.
Yeah, I think once we have these individual terms, it's only now a question of adding all this.
Adding all of these, I think
And
we can
then-
leave it
So
as
that
a,
can be a good homework for.
yes.
Correct?
I agree.
Yeah.
I agree. Because it is also similar to what we did.
Yes, yes.
So, but while you were doing this, I just realized a couple of things.
Please.
So, the zero or the pole can be either negative or positive, right? We got some negative, we think we had examples where we had a negative 0 and a positive pole and so on.
Yeah.
So, like I was looking at 1 plus j by omega, j omega by 20, no?
Yeah.
It went up at 20 dB per decade.
Correct.
Actually, even if you had the 0 as 1 minus j omega by 20, it will go as plus 20 dB per decade.
Yeah.
So the way to distinguish between a positive 0 and a negative 0 is to look at the phase plot, which we have not plotted here.
Correct.
But students should learn to plot that as well.
Correct.
We did it last time.
Correct.
It gets very complicated when you have so many poles
Yes.
and zeros.
Yes.
Right?
Yeah.
So it is when you have more than a couple of poles and zeros, it is sometimes easier to use a tool to plot it.
Yes.
Correct?
Correct.
And same thing for a pole as well.
Yes.
The way to distinguish between a negative pole and a positive pole is looking at the phase plot.
Exactly. Exactly. Yeah. So similarly, the phase also we will give this as a homework.
Yes.
because it's very similar.
Correct. Correct.
They will be getting bored if
Yes.
we. Yeah. So shall we take something new?
We'll take something new. So maybe let us say I only have one pole and one zero.
Uh-huh.
Something slightly different.
So some general.
General case.
So h of s is equal to.
Let us say 1 plus s by
Z1.
Z1
Yeah.
by 1 plus s by P1.
Okay.
And we'll consider two cases. One when the pole is smaller than the zero. Let's start with that.
Yeah.
We will maybe give the other one as homework.
Correct.
Right.
So the pole is
Less than the zero.
less than the 0.
P1 is less than Z1.
Yeah.
Correct.
So h of j omega dB just for the completeness
Correct. Very important.
divided by 1 plus j omega by P1.
Best thing to do is do step by step. You
Yes.
will not make any mistakes.
Yes.
Correct.
Otherwise, it will be a temporary happiness we will have, but there may be a mistake.
There will be a mistake. Correct.
So, pole comes first.
Correct.
So, let's say P1 is somewhere here and Z1 is.
Correct.
So, P1 means till this point no gain.
Correct.
Then there will be minus 20 dB per decade.
Minus 20 dB per decade. Correct. Correct.
It's supposed to go like that.
It will suppose if you only had the pole, it will continue to go like
Correct. So, but here it comes the Z1, effect of Z1. So, if it was Z1 alone, we would have drawn 0 till here
Correct.
and then plus 20 dB per
That's
decade.
right.
Now, since both are there, summation will become
A flat.
a flat from here.
Correct.
So, h of j omega in dB will be something like this.
That's correct.
Maybe we should look at the phase also.
Let's do that. Because we just finished telling them that it's important to look at the
Correct,
phase.
correct.
We will look at that. Actually, they will learn how important phase is when they do the control systems course. no?
Yes.
Because the phase of the system is very important.
Yes. Yeah. Because the same gain, it may be 180 degree or opposite.
Correct.
So,
Correct.
phi in degree. So, what we have learned is where under the P1, there will be the phase will be close to minus 45 degree.
Correct.
So, it may be something like this. And then it was supposed to go to minus 90.
Minus 90. Correct.
But what happens here is Z1 will have
Correct. We'll also add phase
in the positive direction.
in the positive direction now. Correct. And at Z1, it will give you minus 45.
Yes.
Right.
Yeah.
Sorry, it will
Plus
add 45. It will add plus 45.
Yeah, plus 45.
So, the total phase will go to minus 45.
Correct. So, it will not allow it to go just like that.
Correct.
My drawing is not perfect, but
No,
will
but
be
I think we'll just mark 2-3 points, students will understand.
Yeah.
Because the phase is inherently non-linear.
correct. It will be approximately like this,
Correct.
minus 45 degrees.
Correct.
And finally, it will go to 0 phase.
Zero phase, correct. And at Z1, it will be minus 45, correct.
Yes.
At both P1 and Z1,
Yes.
it will be minus 45.
Yes.
As long as Z1 is much, much larger than P1.
Correct.
The closer they get, it will deviate.
Yes.
It will start deviating.
Yes. That also decides how much it will go down.
Correct. That is correct.
But approximately it will be something like that. But I've seen there are some nice online tools where we can plot Bode plot and see
Oh, nice.
for
Okay.
each. I mean, most of the transfer functions, how it generates quite well.
Okay.
So maybe students can try out that.
Sure. I think so. I think it is very useful.
Yeah.
They should try out different
Yes.
types of zeros and poles. Right. In fact, so we have looked at examples where we had a pole at the origin.
Correct.
They can see what will happen if you have a zero at the origin.
Correct. Correct.
They can try out all kinds of
Correct.
nice things.
Correct. So I think this kind of situations will come in the future in some of the other courses.
Correct. Definitely.
Where you are correcting the presence of a pole and so on.
That's true. That's true.
We'll try one more thing.
Sure. This time, I am not going to give the transfer function directly. So we'll give the circuit.
Okay.
And then derive the transfer function and then plot.
Okay.
So let us take something that they have seen before.
Earlier we have seen low pass filter.
Low pass filter.
Yeah.
Let's do one thing. We'll take the voltage across the resistor.
So we will interchange the components.
We'll interchange the components.
Okay. Oh, sorry. See here.
Yes, correct.
Okay, so V naught of S is V naught of S divided by R plus 1 by CS
Correct.
into R.
Correct.
So H of S R by 1 plus RCS. Something wrong?
Into SC, I think.
The denominator will go to.
Correct. Correct.
Correct. So H of j omega is RC, actually j omega RC.
Correct.
Divided by 1 plus j omega RC.
Correct. So it looks like it has 1 0 and 1 pole.
Yeah.
And what I asked for, no? A 0 at the origin.
Yes, yes,
I
yes.
was just saying.
Yes.
Looks like that.
So in fact, this one we plotted earlier.
Correct.
For the low pass filter.
For the low pass filter. That's correct.
Now there is this additional term.
Correct.
At origin. Or
correct.
It will pass through.
It will be a 0
at
the
maybe
origin.
we will take a case of R equal to C equal to 1.
Sure.
The values.
Sure. We'll do that.
Just for the ease of.
Correct. To make it easy to plot. We'll
Yeah.
plot the normalized
Correct.
curve.
So this term will be 0 at omega equal to 1.
Correct.
Until that, I mean, as omega increases, this is going to increase.
It's going to
at plus
increase.
20 dB per decade. So I can draw something like that.
Correct. It will cross the 0 dB point at 1.
Yes.
Technically 1 over RC.
Correct.
But here we have chosen R equal to
C equal to 1.
Correct. So at 1.
Okay. Then at the same frequency.
Correct.
I mean, wherever it crosses 0.
Correct.
You have a pole.
We have a pole.
So that pole will introduce something at minus 20.
Correct.
So these two will get
These
cancelled.
will cancel. So you will just get a line at 0 dB.
Line at
Flat
0
line.
dB.
Correct.
Okay. So this is a high pass filter.
This is a high pass filter.
Passing the high frequencies.
Correct. Correct.
So the phase, so also, I mean, the numerator will introduce plus 90.
Correct. Plus 90 degrees.
and at this frequency, I mean at the pole, it will come down to
correct. It will come down to 45 degrees.
Correct.
And then come down to zero,
Zero.
at
Yes.
very high frequencies.
Yes. So it will start at 90 and
Come down
but
to zero.
zero.
Correct.
So basically at very high frequency, this is almost like a short circuit.
That is correct. 1 over j omega c, magnitude is goes
Yes.
to zero.
Yes. Yes.
That is correct.
So there is no phase, there is no magnitude change also. Everything makes sense.
Correct.
Again, phase I'm not drawing. It's
Yeah.